So now, in principle, you are leave. I don't know. Will you message to Luca if he is joining, or how does it work?
I messaged to him. I didn't get any reply.
Yeah, okay.
So
Well, then it's up to you. So now you are everything is being recorded on YouTube.
okay, maybe we can just start and then Luca joins, or I can call him and ask.
Okay.
Maybe I'll just do that. Hello? Yeah, he's joining.
Then we will wait for him for a little bit.
Yeah.
How is life in UK, by the way?
It's fine. I'm kind of oscillating between Bristol and Portsmouth.
No language barrier, I guess.
Yeah,
Everyone speaks English.
Yes. So that's very good actually. My wife enjoys much more than me because she had no troubles in the laboratory because earlier she's in biology, right? So in Japan she had trouble. Even all the chemical names used to be written in Japanese. So if she wants to take if she has to take something, some bottle like some sulfuric acid or something, so they write in Japanese. Every time she has to translate or ask people, it's a mess. Here it's better.
Yeah.
Yeah.
This sounds like to be a bit cumbersome.
Yeah, and also in Japan, it was language is quite difficult, so it's to communicate, and so yeah, here it is better. But well, the good thing is all the instruments are the same, by the way. So it's only that it's the same instruments. Actually, mostly all the biological instruments are made by Japanese companies. So,
Yes.
but there everything is written in Japanese. Here it's in English. So.
Fine. This sounds like good improvement. Well, definitely for theoretical science, it's not a big deal. I mean, whatever language is written, what can be written.
Yeah.
The only thing which I'm missing when I come to canteen, I don't know what kind of dumplings I'm taking, but I'm taking randomly.
But it's fine. You are not vegetarian, right? So.
No, I mean, I'm not everything, but generically, I may have some preference still. Or maybe instead I want to avoid vegetarian, you know. And then, but yeah, this, I'm not sure, by the way, that vegetarian there is a good life, but maybe it is, I'm not sure.
So it's a holiday time in China, right? Or you are taking holiday? Everyone working.
You know, it's kind of holy to be busy. Even most of our secretaries are.
Your voice is breaking for some reason.
Yes, it's.
Hello.
Well, technically it's possible. I'm not sure that.
So we are live, basically.
Hi.
Yeah, we are live.
Okay, so we're gonna do twice your talk.
Hope it will not be boring.
No, even triple. Because Sravan said that he has an idea to send a message to people that after all those technical troubles, talk was recorded finally.
Okay.
So
Only one thing, guys. I mean, around 6:10, 6:15 I have to go.
And what time is now?
In 1 hour, basically, I need to go.
Then
Okay.
why should we, well, let's say
1 hour talk.
no talk, but there is also something we want to discuss the logistics, right?
Okay, then let's do, I mean, by 6:30
Yeah,
I need to be one place. I think it takes me 10 minutes walk. So in principle, 1
Okay,
hour
then-
and
then-
50 minutes.
Well, then it's fine. I mean, I can talk, but then you can join and we discuss the logistics for next time, how to.
Yeah, okay, let's start the talk now. And after the talk, we do the logistics.
Okay.
yeah, sure. It is for sure like this, yes.
Okay.
Even if we have no time for logistics, it's fine. We can move.
Yeah.
Can I introduce the speaker?
Sure.
Hello, everybody.
So
Look, I know it's recorded. You will oblige me to cut it if you
I
will
mean, hello,
introduce.
everybody. It's four of us, so it's okay.
But you start, you can edit it, right? When you make it online, so you can.
After 1 day.
Okay. But yeah.
No, I just prohibition from Google. It doesn't allow you to do anything.
Okay, but anyway, please, Alex, you can introduce the speaker.
No. You do it. You started very great.
I'll
Now,
give me access for share screen. I cannot share screen now. I mean, it was the trouble before, right? I mean,
yeah, that was actually very strange because we entered Zoom and we couldn't share anything.
yeah,
That's
because
very-
Zoom just works automatically without host, and then it is Alexi who did not give access. It was really crazy. So everyone asking, where is Alexi? Almost 50 people asking, where is Alexi?
No, at some point people were even worrying whether you were still alive or not because it was very. Even Anna didn't know where you were. So I mean.
This is true.
By the way, it's 5:10. Let's start now. It's just
No, Alexi, I think you need to make me co-host this tablet,
Okay.
iPad.
Everyone can be co-host in this meeting.
Yeah.
Good.
Not yet. Now I'm co-host.
Good.
I increased 3 more slides to compare to last time.
Yeah.
I
So
think-
Luca, take this opportunity to say hello, everybody.
Okay.
You
Hello,
missed
everybody. Today is a great pleasure for us to have one of our co-organizer giving a seminar. And Sravan is going to tell us about how to, let's say, make sense of quantum field theory in curved space-time. And maybe we'll tell us something new about this topic. So thank you very much, Sravan. Please, the stage is yours.
Okay, thank you, Luca. So it's nice to talk in our own seminar series, but I would like to speak about some of the series of works which are done in collaboration with Gio Marto on a different formulation of QFT in curved spacetime. Most of the work is actually quite inspired from several talks in the seminar series. So I thank all the speakers of the seminar series before I start the talk. So basically, when we talk about quantum gravity, there are 3 big questions involved. One is about singularities. How do we avoid singularities? That means basically, how do we modify general relativity to avoid singularities? That's the one research area. Then another one is a big question. What is quantum gravity? What is Planck scale physics? Or if there is any unification of all fundamental forces of nature. Then there is a third question, which is much more, it comes even before the Planck scales, even before the singularity regimes, that is quantum field theory in curved spacetime. It is quite an important subject for if we want to build a consistent theory of quantum gravity. So that's what this talk is completely focused on. So there is a message actually I want to convey here in recent series of works with Alexei Koshlev and Alexei Starobinsky, where we have showed that just having quantum gravity, which is renormalizable and unitary in around Minkowski spacetime, is not enough to describe our universe. So we need to care about effects of curved spacetime. So we need to, just because if we have some quantum theory of gravity, we can just immediately apply to our universe and understand everything. No, this is not the case. So if
Sorry,
you
Sravan.
Yeah.
I have a question here. A comment question. So, in general, the property of renormalizability is independent of the background because it's just a background independent statement. Here, what you mean is that before even asking renormalizability of quantum gravity, we should first understand quantum fields in curved space.
Yeah.
That's what you mean.
That's what I mean. Well, of course, renormalizability, it is independent, but mostly the practice of understanding renormalizability is confined to Minkowski spacetime.
Sure. But the fact that
Yeah,
renormalizable is background. Once you couple a theory of gravity, which is of course renormalizable, then is a background independent statement.
Yeah. That's true. Okay, so well, the main point is QFTCS, which is a short form of quantum field theory in curved spacetime, is an important topic. Okay, once we set up the topic, this one I hope we recognize now that it is important. Then there are a lot of questions up here. QFT is a very heart of the quantum field theory. Like, for example, all the things, all the standard model of particle physics is built on the foundations of quantum field theory. So one of the important thing in quantum field theory is the in discrete space-time transformations. For example, CPT. QFT, standard QFT in Minkowski spacetime is CPT invariant, which is well known. So then the open question is, what happens to CPT invariance in curved spacetime? This question has popped up in several investigations for in the context of cosmology and black hole physics. And if you, the one example is in the seminal papers of Hawking in 1975 and 76 about black hole radiation, which is known as Hawking radiation, concerned about the status of CPT in the context of black hole physics. And Gerard 't Hooft has been advocating to the subject for several decades. And so this is an open question which has bothered really generations of physicists. Here at this point, I would like to point out the two important papers, even before a full formulation of QFT. So actually the status of describing particles in curved spacetimes has been identified as a big problem. So one of the seminal paper is by Schrödinger, who with a paper titled Expanding Universes, has asked the question of how to describe quantum particle in de Sitter space. And Einstein's and Rosen's paper again concerns about particle problem in general relativity. So again, all these investigations point out really basic questions involved in these subjects. Again, so just to show the importance of it, in standard quantum field theory, we basically understand particles and antiparticles as the following. So antiparticles are basically the particle states which go backward in time. So which is according to the Feynman's famous interpretation. Well, the point I'm trying to highlight is the concept of backward in time. So the question is basically, we fully understand the meaning of backward in time in the standard QFT, but surely time reversal operation is something not clear in curved spacetime. So this is something an open question. And as I explained already, CPT is an open question. And again, if we ask why QFT in curved spacetime is very problematic, so isn't it obvious? Like, okay, you can simply construct how you construct QFT in Minkowski spacetime, you just construct in some curved spacetime. So why is it so difficult? Well, one way to show why it is indeed a difficult is basically the concept of time. in general relativity is totally different from quantum theory. In quantum theory, time is a parameter. In general relativity, it's coordinate, and we have basically often have the dynamics of space-time. So given some solutions for a particular background, so this makes it difficult. Again, another indication that gravity is indeed a special, I mean quantum gravity, because the one of the most basic equation associated with quantum gravity is relativity equation, and there exists a problem of time. It has been there for decades and bothering us physicists how to treat time in the context of gravity, because the reason it appears is that you have this relativity equation which looks way more different from Schrodinger equation. As you see here, the psi is the wave function of the universe, H describes the Hamiltonian of gravity, and there is no time appearing in this equation. So this kind of indicates time may be a special entity in the context of gravity. Now, let us revisit that what is meaning of time reversal in our standard understanding of quantum theory. So time reversal in quantum theory is associated with anti-unitary operation, as we know from the seminal works of Wigner. So in quantum mechanics or quantum field theory, we always do things with unitary operations, but time reversal is a very special thing. It is anti-unitary. So if you pay attention to the recent observations made by Donoghue and Menages in the recent years, in quantum theory, the sign of I, the complex number, play a very important role. Suppose if you change I to minus I everywhere, we change the conventional error of causality. So I will explain in a bit what this means. So let us look at, for example, Schrodinger equation. The way we write is in this form. This is the Schrodinger equation. And once we have the Schrodinger equation, what we define are basically the positive energy states. So suppose you have some Hamiltonian which has some eigenvalues, and then you have time evolution of a state is described by this, which is exponential of minus IET, and you call it as a positive energy state. And suppose if you decide to write, okay, well, no, this is not my Schrodinger equation, I just want to write, for example, instead of I minus I, you can write the Schrodinger equation like this. Well, I denote this with this is a conventional one, and this is basically the unconventional choice. And then you ask a question, do you change anything? Well, you don't change anything about quantum mechanics, but of course you change a bit your definitions. Now you can call the positive energy state to be something with exponential of IET. Well, these both are same. If you do, for example, if you say that this definition is associated with your conventional notion of time direction to be minus infinity to infinity, and well, it's a positive energy state. Equivalently, this one is a positive energy state, but you just reverse your conventional notion of time to unconventional one. So that means these two are equivalent. So it's just the only difference is your time arrow has changed, and this is associated with changing your plus to minus sign in your equation. This is quite an important observation, and I will explain in a later step how this can be useful in understanding several things in the context of cloud spacetime. Now, let's get back to again QFT in cloud spacetime. So what does it mean? So let's define it. It is basically GR plus quantum mechanics. Well, this gives a stage what I am talking about. So it's I'm not going to any modified gravity, so I stick to GR and quantum mechanics, and what is basically the curved spacetime, QFT in curved spacetime, by combining these two theories. Quantum gravity is basically is a later question, in my opinion. Is because the following: QFT in curved spacetime is just a formulation without worrying about much about the renormalizability and etc. So what we really want to understand is unitarity. rather than all the renormalizability and UV finiteness. So that is ultimately the question of quantum gravity, so which needs to be understood. But surely there is a great deal of physics we can learn from this subject. So if we want to see in some analogy with the historical development, well, special relativity and quantum mechanics, if you combine them, you get Q15 Minkowski spacetime, which is a precursor to the full standard model, the understanding of the degrees of freedom in nature and renormalizability. So this comes first. So this setup in what we are talking about, Q15 cloud spacetime. Of course, I restrict to the perturbative QFT, so not non-perturbative. So I mean, it's important to understand. Of course, when there is a non-perturbative regime, so surely there are complications. We need those are later questions. Okay, so coming back to the how special relativity and quantum mechanics are merged. Indeed, these two are totally different theories, but the way we merge it is basically using commutation relations, commutation and non-commutative relations. So the so-called the position and momentum commutation relation we generalize to the field and conjugate momenta relations. But most important thing, the way we combine special relativity and quantum mechanics is by learning about space-like events, separated events. So the thing in the construction of Q15 Minkowski spacetime, we demand that any operators corresponding to space-like distances should commute. This tells us clearly, suppose if you have a scalar field, if you want to quantize it, you promote the scalar field to an operator and you expand in terms of creation and annihilation operators with some set of mode functions. And how the way you expand in terms of creation and annihilation operators is dictated by this demand. So this is, you can, I refer to this, for example, most well-known book of QFT by Srednicki, which explains this very well. Also many other books. Well, surely what I want to draw your attention here is the space-like distances, which are very natural to occur in the context of cloud spacetime. So that's where a lot of conundrums happen. So we need to understand it much more at a deeper level. So now I will jump to one of the most famous cloud spacetime, which is de Sitter spacetime. And de Sitter spacetime can be expressed in several ways. Well, one of the ways de Sitter spacetime can be written is in the flat FLRW coordinates. So de Sitter spacetime is one of the very important spacetime because it has the same symmetries as Minkowski.
May I ask you here?
Yeah.
I'm literally confused a little bit.
Yeah.
So I understand that you say that quantum field theory, in your point of view, is special relativity plus quantum mechanics.
Yeah.
Okay, well, this I can kind of accept, even though I don't understand this statement, but let it be. But what I really don't understand, now you jump to GR, and now you already jump to very famous, let's say, kind of Friedman universe or de Sitter space. And generically, general relativity allows you any space-time with or without time, with any signature. Not well, maybe metric. First of all, you even accept that your space-time is a metric space.
Yeah.
Most likely Riemannian.
Yeah.
And why do you think this all holds?
It's so.
Well, what do you mean it's so? No, okay, let it be Riemannian, maybe. If metric, okay, but why do you, for example, Elmas by definition say that there is one minus and all the other plus eigenvalues of the metric? GR allows you to have anything. Generically,
Yeah,
geometry can be
it
anything.
is true. It is true. It is true. GR can allow anything, and of course, it depends on what you insert on the right hand side of Einstein equation, some matter. Okay, and you can have wide class of space times. But here, the context I'm speaking about is basically how to understand quantum fields in a given curved space-time. And for the moment, I assume there is no back reaction. So just try to define. I want to define some curved space-time and try to see if I can quantize some field in this space-time. For example, I take it as some scalar field in this case. So the thing I'm pointing it out is we know very well how, given Minkowski space-time, we know how to quantize. And then here in curved spacetime, it's a bit more tricky. So this is what I want to point out.
Oh, this is for sure. It's much more tricky. This I don't know.
Yes, and surely
No doubt.
think about any curved spacetime. So well, we need to understand step by step. So I start with de Sitter spacetime. Of course, then I will try to see whether the scheme, how this scheme can be propagated into any curved spacetimes, any other complicated spacetimes, but I will mention about them. But surely I'm not talking about anything. I cannot define quantum fields of any curved spacetime, so which is quite difficult task.
Okay. And maybe question about even next slide. I don't know what will be the next slide, but still. Here you write something in, no, it's okay. I'm just curious. You write immediately the sequence in, let's say, standard cosmic time coordinate, then you come to conformal time.
Yeah.
Fine. And what will happen if I go to any other coordinate patch? For example, static de Sitter, which looks like a black hole.
I will surely speak about black holes. So, but
No, I mean just if you rewrite de Sitter as in static coordinates, and what?
I think I will answer this question when I speak about black holes. So I can answer.
Okay. Okay. Good. Thank you.
And here, the choice I took for the FLR flat FLRW is basically in the few slides I will talk about inflation. So it is the metric which is useful to understand cosmology rather than static de Sitter space. It is one of the reason is this metric, this basically toy metric, will describe expanding universe and also the co-moving observers. So when I specify metric in particular coordinate system, it basically gives the view of some observer who is not part of the quantum system, just some co-moving observer who is seeing how the horizon is changing with time. So yeah, surely what I have in mind is cosmology, especially early universe cosmology. So hope it's clear. Then, so can I proceed, Alexei?
Yes, thank you.
Okay, so when we write de Sitter FLRW, we write like this, and usually here the scale factor, we denote it as exponential of HD. But then you see another step here. Well, we go from this form of metric to this form of metric. The reason we do it is because this form of metric is useful to quantize a field. Let me explain what it means. Suppose if you take a Klein-Gordon field and massless Klein-Gordon field, so basically you have square root of minus g. Well, there is also d4x. So we basically understand everything about harmonic oscillator, QFT in Minkowski spacetime. Okay, so QFT in total spacetime directly, we cannot, of course, quantizing directly this field is very difficult and we don't know how to do that. But then there is a trick. The trick is basically we write, given this metric, we write this box operator, and then we redefine the scalar field. When we redefine it, we go to basically this conformal time. And then this metric, this Klein Gordon field Lagrangian action will become this in a redefined redefined scalar field. Okay, so I should put phi tilde, but I just for to avoid confusion. So basically, you obtain this by this redefinition. Then you can understand quantization quite easily, because when you look at this looks like some effective scalar field with time dependent mass. So why you get time dependent mass? This is exactly because this is a curved spacetime. So if you look at this is a spacetime, it is conformal to some Minkowski, right? So it looks like quite a simple spacetime, right? And when we do quantization, again, when we bring it to this form, and then we basically follow some intuition based on our understanding of QFT. But here there is something in a standard quantization. We take two assumptions. One assumption is that the sign of this conformal time should be negative, and the h, which is called the Hubble parameter, it has to be positive. So these two assumptions we automatically take. But then if you look at the metric, this is not what it is, because the metric is completely h square and tau square. Then you ask a very fundamental question: how come quantum fields aware of this sign? Remember, time is a parameter in quantum theory. So how come quantum fields can recognize and feel that this metric, they should only follow tau less than 0 and h greater than 0, but the metric doesn't say anything about this. So this is when a very crucial point we take in this as an initial assumption. Okay, as I explained before, so what is the meaning of this metric?
Sorry, Sravan.
Yeah.
How do you see the if you want to see like the region tau greater than 0 and tau smaller than 0 in terms of t, what would be the correspondence?
Yeah, so good question. So, well, basically, tau is defined to be integral dt by a.
Yeah, so tau greater than 0 means?
Tau greater. So basically, when you take this assumption of h greater than 0, okay.
I mean, there should be some interval, some extreme of integration in the interval, right? Which
yes.
depends on t.
Well, yeah, but of course, well, you can put some limits on your integration, but basically, you get when you do this integration, you get tau to be minus 1 over ah, and if h is greater than 0, tau is less than 0.
So which h, the h of t?
Well, h is usually taken to be a constant, so it is a dot by a.
Yeah, so is the h that is in the exponential of e exponential of t. Sorry,
Exactly.
the exponential ht.
Exactly.
So tau greater than 0 means the exponential is.
I will explain it. I will explain in a moment.
Okay.
Your point. Well, here we want to model expanding universe, right? What is the meaning of expanding universe? The scale factor a is growing. Okay, that's what expansion means. So your spatial size of the universe is changing and it is growing in size. So then when you look at this, I will come to this exact point, the meaning of expansion. So, and these two definitions of that. So just hold on with me for a minute. So if you look at this spacetime, so this results in some horizon, the co-moving horizon. So suppose if you are an observer in the center, like
Sravan, may I just ask you a technical question? Maybe I'm missing something trivial. In your last formula on the slide, this integral, where is h there? Is it there? Is it true that h is not there in this? I mean, that this action doesn't depend on h.
Yeah, h expression doesn't depend on h. Yeah, it kind of depends because your tau is nothing.
No, but wait a second. But then, and then who is k in this expression?
K is the wave number. So basically, you write it in terms of Fourier modes
Fourier modes of what?
of phi.
Oh, okay, 5. It's okay. In what? In space coordinates?
Yes.
Okay, so this is 3 vector. So
Yes.
k is a 3 vector, and k squared is just
Yes.
3 vector squared, and for simplicity, it's partially flat.
Yeah.
Okay. Okay.
That basically you have phi of tau x. You write it as phi k of tau exponential of ikx. This Fourier transform. So it's d cube k. So phi k is of tau is the Fourier mode. So basically that's what phi k is. I suppressed all these indices, but this is how you standardly take your action into.
But it should be integral in d3k, not d3x, right? No? Or d3.
Now this is phi k, right? So you basically you write, well, this is d4x, and you write phi of x tau to be phi is function of space and time, right?
Yeah.
Okay, then you'd write it as an integral. So of phi k of tau, so exponential of ikx. So of course there is 1 over 2 pi whole power 3 by 2, and there is a
That's why there is a delta which disappear, right?
Right,
Which
right.
makes the integral disappear.
Yeah.
Delta of x. Anyway.
Yeah. So okay.
Let's go on.
Okay, then I'm going a bit slow, but I hope it's okay. So basically, when you have this metric, you have a horizon, co-moving horizon. Okay, that means how far the distance light can travel, right? So the maximum distance light can travel defines a radius, and the radius is given by this modulus of 1 over ah. So basically, when you have x scale factor is growing, your horizon radius, which is co-moving horizon radius, shrinks. So that defines expansion. So the expansion actually basically defined by the scale factor. Let me give you a reference. If you go to Wheeler-DeWitt equation, your wave function of universe is function of scale factor and all the fields in your universe. There is no time appears there. So the clock that tells you about events happening in your universe is the scale factor and the fields. Okay. And if you look at this picture, what is interesting is that there are causally disconnected points every time at any moment of expansion, and these causally disconnected points are exactly those parity conjugate points as you define, you see here. You think of it as a sphere, and you have 2 points, pi phi and theta phi, and pi minus theta and phi plus phi. Those are parity conjugate points, and they are separated by 2 times the horizon distance, so they are causally separated. Okay, this is how a co-moving observer sees the space-time. Now, again, come back to the same metric. Now I will answer your question, Luca. Okay, so if you look at this, you call it as expansion. If you assume t runs from minus infinity to infinity, so it is our conscious assumption, and then h is greater than 0, then you say tau is less than 0. This is standard way, the way people assume it. Okay, well, of course, then you ask a question, well, this is de Sitter space, right? And de Sitter space has curvatures, and all the curvatures are basically the function of h square, not just h. Okay, so there is no reason to assume that h is greater than 0 in principle. So because everything is symmetric under h2 minus h, there is a discrete symmetry. Okay, and suppose you, for example, if you look at the scale factor, if you reverse the sign of h and sign of t, the direction of t, your assumption, still this remains intact, right? Your exponential of ht remains exponential of ht. If you change t infinity to minus infinity, h less than 0, you get tau greater than 0. So you have 2 realizations of expanding universe, 2 different realizations. So, well, this was actually quite noticed by Schrodinger himself, and who was troubled by the fact that how come you have 2 possible realizations of expanding universes. So that's why he wrote this article, Expanding Universes. And Schrodinger proposal was that no, there cannot be two expanding universes, so there should be just one universe. That's what we observe. Well, then there is a proposal by Schrodinger, which I will not speak about here because the context is quite different. So here is the point that there is, the point I want to highlight here is that if you want to do a time reversal in digital space-time, when I say time reversal, if you look at this metric, what are the discrete transformations of the metric? Okay, tau, that means that the discrete flips, which makes the metric invariant. Tau goes to minus tau, x goes to minus x. Then your metric is completely invariant, right? Then, so normally the common intuition is that when you look at the papers or books about time reversal of expanding universe is usually thought as contracting universe, but not so. You call it as contraction if you keep h sign of h but only reverse t. Yes, then scale factor is decreasing. But if you reverse both signs, you still have the same expanding universe. You don't change anything. Now we ask a question. Okay, well, first of all, wherever there is a discrete flip, that means that is something associated with quantum theory than classical physics. Here, classical physics is just expansion. Okay, so time actually does not play a role much here. So expansion is characterized by the growth of the scale factor. So then what we do here, suppose let us, because you see, when you look at this metric has the symmetry, and it is when you define quantum fields in this metric, it is quite non-trivial to ask that say that okay, your sign of tau should be less than 0, but quantum fields cannot feel any difference. Okay, that means suppose why don't we make a simple step? The simple step is the following: can we have quantum field operators which respect this discrete symmetry? Well, you can ask the question why I want to do it. Well, I will explain later why I want to do it. But we always driven by symmetries, right? We want to, it's not a bad thing to ask if there is a symmetry of your metric, and ask all the operators in your quantum theory has to be symmetric, dictated by the symmetries of the metric, right? So this is what we ask. But can we do it? Okay, so to do this, it is quite non-trivial task. But there exists a mathematical operation called direct sum, which allow us to express the field operators which are symmetric under discrete transformations. Again, I want to point out here is that we are talking about expanding universe. When we take a discrete space-time transformations, it is same expanding universe, right? Because we change both t and h sign, that means tau sign. Okay, so it's the same expanding universe. Now, when I express the field operator phi of tau x as direct sum of two components. So direct sum means basically when you have two operators expressed as direct sum, they go into the matrix form in the block diagonal way. Okay, well then, this is just a mathematical operation. Then you ask a question, what I'm doing physically. So in quantum theory, basically it's not just time reversal is not that important, but it's basically the CPT is the most important thing, the combined operation of these three. Here we talk about chargeless fields, so it remains PT. So phi 1 is a component of the field at positive x spatial points, and it gives the fields with positive energy which propagate forward in time, and phi 2 is a component of the field, the same field, but it propagates backward. It gives fields propagate positive energy states propagate backward in time. So this is the construction. That means the field itself doesn't have a unique direction of time evolution, because time is a parameter here. So what we do here is, if we given a spatial region and we cut the spatial region into two parts, and then say that if you have a quantum field that is basically evolves forward in time in the one region, and in the parity conjugate region, it evolves backward in time. So this is what this splitting will tell us. And of course, you need to implement this. Well, it's not just the direct sum, then you need to implement this defining the vacuum, and defining the vacuum is defined by the annihilation operators acting on the vacuum must be 0. Then basically the vacuum is direct sum, and then you have in the matrix form, this looks like this. And this phi1, phi2, which are basically same description of the field of components, right? And these two components must commute. And this is how we define it. We have direct sum field and direct sum vacuum dictated by these rules. Then what? Then you can ask a question: what is being done here? Is basically
if you just take flat space fields, like fields in Minkowski space, we know that their CPT, or like PT for fields without charge, is respected. Okay, and in that case, we don't need to do this, of course.
I will explain. No,
sure. I mean, in general, you don't need to do that. And the field itself is already PT invariant.
No, it's not.
So even there, you say there is a problem in the way we define the field.
Yeah, even in the Minkowski, field operator is never PT invariant.
Okay, so it's not just a problem with the zeta. So in principle,
yeah.
I mean,
well, there's no problem per se. I mean, there is a way.
There's no problem, of course. What we want to do is not, you want to change something, not only in the zeta, but even in flat space.
Yeah, but that it is just a change which does not have any observational implications. But
no. But in principle, why do we need to change the field to respect this double?
Well, it is
just think about Minkowski. Why would you do that?
I will explain. Why is a good question, but well, then you can first of all, whether you can do it or not you have to do the consistency check. Okay. But
the motivation. What is the precise motivation?
I will explain the motivation clearly. I will explain. Just hold on just a couple of minutes. But if the construction is clear, then I will go to that. Okay.
No, I think this construction is just what is the motivation that you need to write the field in this way?
Well, first, okay. Well, their motivations come from seeing several complications you see in crowd spacetime. But then before I want to explain.
But so far, you haven't explained it, right?
I haven't explained.
None of these complications.
No, I haven't explained the complications. Yes, I'm just explaining what are the trivial steps you can take. Okay, so it's always like sometimes when we take some very simple in mathematics, when you take a very simple step, it leads to quite a totally different understanding of physics. So I will arrive at that point, but I want to explain there is a different way to do it. Okay, but the advantage of this construction is that you do not have your assumed notion of time here, because you see normally your count of time is basically minus infinity to infinity or infinity to minus infinity. You do not have any notion of error of causality here, because this construction completely agnostic to that. Construction respect the symmetry completely. So you do not have any intuition before you do quantization. Your quantization is completely independent of your definition of time. Okay, that's one advantage, conceptual advantage, but I will come back to that. Okay, so what this means is basically when you have direct sum means when you have two regions, then if you want to construct a Fock space separately and do not want to mix, do not want to have any superposition of states between these two regions, then direct sum is an operation that will allow you to do that. And this is actually quite known in the old days for in a totally different context, but still in some particle physics context called super selection rule, which was proposed by Weikman and Wigner. Okay, now I come back to your Luca question. This is standard. Of course, here I'm talking about again a direct sum operation in the Minkowski spacetime, but I will explain what is different here. Okay, so if you write the standard quantum field theory, you write, okay, well, basically this is, you write, okay, phi, some phi operator, you write in terms of positive energy and negative energy, right? Then this positive energy and negative energy, you follow the definition of by writing the Schrodinger equation in this form. So this is how you define it. Okay. When you basically apply any PT operation on this, on this, well, this is how your standard way to write it. If you write apply PT operation does not change creation and annihilation operators. So you basically swap this positive energy and negative energy. Okay, so your field operator in the standard quantum field theory in Minkowski is not invariant under PT operation. Well, you can generalize it to CPT as well. Okay, but that's trivial. So now what we do is, okay, well, because you see, there is a statement which is very correct about notion of time in quantum theory. It was
in phi 2 should be B dagger, right?
Yeah, sorry, it's a typo. It's B dagger. Yeah, sorry, it's a typo. So okay, it's B dagger. Now what we do is, okay, we want to write something which is totally PT symmetric. That means basically if you apply PT operation here, you not only change the mode function, you change A dagger and B dagger, A to B. Okay, that means you write, for example, your quantum field is completely PT symmetric, and when you take the direct sum, you describe quantum field in the parity conjugate spatial regions with time forward and time backward evolutions. Here we basically take a different structure of Schrodinger equation, which I will explain in the next slide, which is called the direct sum quantum mechanics. Now you see clearly what is happening here. Basically, if you write the Schrodinger, this is when we want to write the standard Schrodinger equation, Schrodinger ket state, as direct sum of the two. Okay, when you take direct sum, basically it becomes psi1 plus psi1 psi2 as a column vector, right? And if you remember, in the initial equation, we change I to minus I, and then you define positive energy state. You can define in two ways, right? And the second way is in exactly the second line. So basically, in this description, if you have a quantum state, again, it is a direct sum of two parts, and these two parts is basically one is forward in time in one spatial region, and another one is backward in time in another spatial region. And this is how quantum mechanics gets transformed. And now I give you clear motivation here. Okay, now basically in nature we always study physical systems. Well, by the way, here H is the Hamiltonian. Okay, physical systems which are PT symmetric. That means always your Hamiltonian is invariant under PT operation. P is parity and time. T is time reversal. Time reversal is anti-unitary operation. Of course, there is a version of PT symmetric quantum mechanics proposed by Carl Bender, which says that, okay, well, that is a different construction. Okay, well, you can, PT symmetry is the most important thing. Hamiltonian doesn't have to be Hermitian. Well, I'm not talking about that. Okay, I'm not talking about anything related to non-Hermitian Hamiltonian systems. But here the question is a bit more different. Suppose if you have a physical, can we have a physical systems where Hamiltonian is not PT symmetric? Then what will happen to quantum mechanics? Okay, this is the different question. And when Hamiltonian is not PT symmetric but still Hermitian, it is possible. Okay, that means here the question is, can we have physical systems where PT symmetry is broken, and quantum mechanically what does this mean? So the standard Schrodinger equation cannot see anything about the symmetry of the system, because in the standard formulation, your Hamiltonian, for example, your Hamiltonian is PT symmetric, but your wave function is not PT symmetric. Now we prepare a different version of Schrodinger equation. Okay, suppose if you have a Hamiltonian PT symmetric, Then also demand right Schrodinger, the Schrodinger state, the psi, also PT symmetric. This construction allows to study basically where systems where PT symmetry is broken. This is one motivation. And of course, then you can ask question, okay, well, do I have some specific example? I don't know anything in quantum mechanical systems, but in the regular physical systems, but at least in the context of gravity, there is a specific example where PT symmetry is broken. And I am curious to see what this means to the system. So this is one motivation. I will clearly explain that. So I hope this construction is clear. Then I will just want to comment about.
But the motivation is still not clear to me. Why we need to start with fields?
Start with
both type of fields.
Well, first is to demand the symmetry at every stage. Symmetry is
your only motivation that you want to have some fields.
Yeah.
My field which is PT symmetric. That's it.
Yeah. I want to have some fields which is PT symmetric.
Okay.
Once I prepare this, then I will at some point I want to break the PT symmetry, and this will allow to give a construction what is the meaning of breaking PT symmetry, which will result in some effect in physical world. That's one motivation, just one motivation, not all. Okay, and another thing which is again in this construction, which is basically, suppose when I take about de Sitter space, okay, and your horizon is shrinking as the scale factor is growing, right? And when the horizon shrinks, you have a quantum field exiting the horizon. Let's talk about, for example, quantum field exiting the horizon at 2 points, which is theta phi and pi minus theta and pi plus phi. You clearly see that these two are causally separated points, right? Now, when I write as two components, okay, when I write a quantum field as two components, the component exiting here has nothing to do with the component exiting here. So I decouple the system. So that means the physics happening at space-like distances then cannot depend on each other. If you have just one quantum field which is exiting the horizon, that means you are including the space-like distances in the evolution of one quantum field. Here it is split. So in other words, well, I do not have a drawing here. In de Sitter spacetime, if you write in conformal time, the light cone shrinks as the universe expands. As the light cone shrinks, you have the things exiting, going to space-like distances. Okay, when things are when you have a point at causally separated points, if you have some physics is happening, I want to separate this, and this is what I achieve by direct sum description. So this is the second motivation, and I will explain what this means. Okay, I will explain what this leads to. Before I do that, I just comment that, well, this direct sum quantum field theory, again, emphasize it removes our conceived definitions, our assumed definitions about time. So you have, and also our assumed definitions about what is positive energy state, what is negative energy state. You have kind of quite a complex thing. Okay, you basically remove effectively time directions. So which has some interesting implications in the context of quantum gravity, but I will talk about later. Now let's try to come to this picture and what this picture has to offer. Okay, now let's again discuss about de Sitter space. You have some observer, right? You can imagine some observer who is seeing at a given moment of expansion. So if at a given moment of expansion, you have some scale factor, you have observable region of the universe, right? Now you talk about quantum field. Suppose this observer is seeing, because now quantum field is the direct sum in two parity conjugate points. Now you suppose this observer is looking here in this direction, let's say theta phi, and looking at in the other direction pi minus theta and pi plus phi, and the observer sees the direct sum of two states, right? But this, for this observer, it looks like something is lost beyond the horizon. Something is lost, because if the observer look at this direction, okay, there is something is lost. But if you look at another image, by the way, when I say observers, these are all imaginary. Okay, let's imaginary, not part of the quantum system. They're just imaginary, like in the thought experiment. Now, if you have an observer, another observer, just on the border, right? Just on the horizon, the horizon distance. Okay, A and A double prime are causally connected observers, right? Now, but what is happening on the right of this observer is completely invisible to this observer. But according to direct sum quantum field theory, every observer has to see always direct sum of two states, that is phi1 and phi2. So this observer, by definition, has to have phi1 and phi2. That means also when this observer look at this, it looks like something is lost, but the construction tells you that it is the same state which is here. That means everyone happened to see exactly the same thing. In other words, if you want to see what is the meaning of horizon in the direct sum quantum field theory, is basically how horizon acts like a mirror. In a sense, if the observer look at this, although it looks like something is missing and he cannot see it, but if you look at the other side, it is exactly the same state. Okay, that means, I mean, there is nothing you are losing outside your universe. Your universe is your universe, and it is complete by construction. So this is called as observer complementarity. So which has several motivations, but one of the very trouble with the DC space is, okay, if you do not have this construction, if everything is random, okay, then you always have states disappearing out of your horizon. You always have something is missing in the region where you can observe. But suppose you choose a different quantization, but it's not so different. It is a very simple demand. Metric has the symmetry, and write the fields which respect the same symmetry of the metric. It's an extremely simple demand, quite a mathematical demand in a sense. Okay, and physical demand as well, in a sense that you write your Fock space or Hilbert space as direct sum of two, and these two regions are just dictated by parity. So you then you apply time reversal to these two regions. So the observer complementarity is quite consistently achieved with a simple operation, and there are several proposals based on.
Sorry.
Yeah.
So for instance, okay, you have this field made up of phi1 and phi2, but if you are one of these observers, for instance, A1, let's take A1, A prime, sorry, A prime, and you say, okay, I want to go in the laboratory and create particles, okay, from some value state. You can do that. You want to create some particles, and of course, you would just select 1 arrow time, because we know that we are living, we have 1 arrow time going somewhere. So you would.
So again, when you say 1 arrow of time, what?
No, you would choose a convention and say, okay, now I can measure my clock. I know that I have a 1 arrow time. So I will be, I don't know, phi1, for instance. So given I'm phi1, I will create only particle with the A dagger on the vacuum of 1. So for me, what is going to be? I mean, I'm going to create those particles, but there is no way I can create also particles of the other vacuum. The other vacuum is inaccessible to me anyway.
Even though it is inaccessible, okay, well, okay, let me put one point at a time. So if you talk about arrow of time, okay, in the context of universe, the clock is the scale factor. It's not time. It's not the time parameter. Time is a parameter, so it's a different one. Okay, here time is a parameter in quantum theory. Quantum theory is so the arrow of time. There are two different things: thermodynamical arrow of time and quantum mechanical arrow of time. Okay, here, well, thermodynamical means basically, for example, universe is expanding. It's a one direction. That means the scale factor is increasing. So this is one you can think about as kind of time, but it's not exactly the time. Okay. And here again, you are talking about some laboratory. But well, here I'm talking about universe. It's not someone setting up the fields. So you have, for example, what happens in the universe is basically you have universe expansion. Well, due to some initial conditions, whatever they are, but once the universe expands, then the quantum fluctuations are generated everywhere.
No, I'm saying, let's suppose even now, here, there is some Hubble radius, the universe is expanding, and we are sitting somewhere, and you want to...
That means you if you look at one direction, right? So you observe something, okay? Then
No, you create something. You create a particle, for instance.
yeah,
Which
well, you
particle
create
is the dagger or bidagger?
Yeah, you create particles whenever you create particles, okay? What I'm saying is, like, even if something is going on the other side, but you do not lose anything.
No, I'm saying, for instance, if I want to create a particle here, which shall I use, bidagger or a dagger? Only one, right? I cannot choose, I cannot do both.
Well, both combine your full space, okay? Both combine because you see, for example, for this observer, this is the whole region, right? This is the whole region. So every observer has to see phi1 and phi2 as direct sum. That's the rule. So this is basically the radius of this observer, a double prime. And this is basically the radius of this observer at a given moment of expansion, okay? So
yes, I'm saying, but let's suppose I'm here sitting, I'm A1, and I want to create a photon.
okay.
I want to do whatever, want to...
Of course, then if you want to create it, then you basically already break the symmetry of the metric, because you go to a specific point in space-time and you create something.
Yes, so but what I'm saying is that you will choose only one field to do that. The other one will be inaccessible.
If you do go and create in a specific way, and of course you automatically break the symmetry of space-time. Here I'm talking about how random fluctuations, quantum fields in a given space-time, just floating everywhere and respecting the symmetry.
Okay, I think we can discuss later this, because otherwise, because you have 5 minutes. So anyway, let's say 10 minutes.
Okay, well, okay, fine. Then of course you can try to understand scattering in digital space-time, but again, I will skip this part, because when I say scattering, and it is scattering of quantum states happening in a finite interval of time compared to if the scattering is confined within your observable region. But I will skip that part. Okay, well, I want to come back to a very observational effect, which is basically inflation. Inflation is quasi de Sitter expansion. It's not exactly de Sitter, and de Sitter has the symmetry, PT symmetry, but not quasi de Sitter. So PT symmetry is broken. Okay, now what you do basically when you have inflation, so we are at the center of the universe, and we observe lights, photons, CMB photons coming from all directions. Okay, and then all these photons are basically, those are quantum fluctuations generated during inflation, and they exit the horizon, they enter when at the present epoch. So this is what basically you have during inflation. You have the big horizon radius, and then as inflation grows, the co-moving horizon decreases because scale factor increases, and then inflation stops, and then you have the horizon increasing again. So when the horizon increasing again, the point again you get access to the points which you lost during inflation. Okay, so then you have the CMB photons coming in from two opposite directions. Here in this particular picture, A and B, and let's say A is the parity opposite of the B, because you have the CMB sphere, right? So like you think of it as A as a north and B as a south. Well, of course, usually north in the vertical direction, but think about like that. So they are parity opposite points. There is an anomaly which is called hemispherical asymmetry anomaly, which says, well, these pictures may be a bit confusing. Basically what this says is, like, you have observed the sky in one direction. Okay, you observe the sky in the opposite direction. This is basically the power spectrum. Power spectrum is the 2-point correlations of quantum fluctuations generated during inflation. Okay, what is observed is, if you observe in one direction, let's say n hat, and you observe exactly the opposite direction, minus n hat, and the difference is not zero. Okay, if you when do you say isotropy? Isotropy is something like, okay, whatever the direction you see, everything should look the same. Okay, but from the Kobe data, WMAP, Planck, what is consistent observation is that there exists a direction of maximal asymmetry. Okay, you go to you kind of choose the CMB equator. It's all okay, and then look at the north and look at the south, and the difference in the power spectrum is non-zero, which is extremely troubling thing, right? Then it kind of shackles the way what inflation predicts, because inflation predicts isotropy completely. Okay, but then the question is, okay, well, maybe, but this difference is observed to be extremely small, and also this difference is observed to be scale dependent. So I will explain what does it mean in the next slide. Now what we do here, basically, because inflation breaks PT symmetry, here you have a quantum fluctuation in one direction and another direction. Okay, also feels the, because the metric is not PT symmetric. Now you put quantum fields on a PT broken metric. Okay, and the quantum fields kind of emote or feel this PT symmetry broken. And how it is broken? It is exactly broken by the so-called slow roll parameters. Okay, if the slow roll parameters are zero, you get back to de Sitter, exact de Sitter. If the slow roll parameters are non-zero, you get quasi de Sitter. And now what in this construction, the fluctuation which you are receiving from one direction will not be exactly the same one, because these are produced in a vacuums which are PT asymmetric. Okay, and then when they enter, so you kind of measure all this future, right? So quantum fluctuations generated, they are frozen after the horizon exit, and then they enter. They are what is frozen in one direction is not exactly the same in the other direction, because the PT symmetry is broken, and this construction gives a way to have the quantum fields in such a format. Okay, because of this, what is extremely curious is the difference between the two power spectra. You get to be non-zero. Okay, and it is non-zero for the large wavelength modes, those wavelengths which are much greater than the present Hubble radius. Okay, but then if you go to short distance scales, you recover isotropy. That means those modes, those fluctuations which are very large wavelength, basically feel the effects of gravity, because if you have some horizon, okay, if you are deep inside the horizon, you have local Minkowski. That means everything is isotropic. So then you have a PT asymmetric expansion, which is effects are happening at the horizon scales. And if you go to those particular wavelengths, then you kind of generate an asymmetry. And this, you exactly get it. And this curve is what is surprisingly what experimentalists are expecting.
Sorry, Sravan.
Yeah.
Do you have an expression for this P zeta? Where is the difference?
Difference is of the order of slow roll parameter. The expression is there in the paper. Okay, well, I can give you something.
It's like why they're different. Okay.
P zeta 1 is something like h square by 8 pi epsilon. Let me put modulus here, plus ns minus 1, some function of k. Okay, P zeta 2 is again exactly the same, h square by 8 pi epsilon minus ns minus 1, some function of k, right? If you take the difference, the first term cancels, the leading order term. Then there is a subleading order.
Why there is this minus appearing there? Because you're taking some transformation. I mean,
yes, minus appearing there is because quantum mechanically we break the vacuum. We choose a vacuum, okay, that breaks the PT symmetry. That means the slow roll parameters take a discrete clip to define a vacuum. You define a different vacuum. Okay, if you don't do this step, then you basically have the identical vacuums in the two regions of space, and then basically you do not have any difference. You again predict an isotropic power spectrum. But here we propose a different vacuums because what are the parameters responsible for breaking PT symmetry? Those are the slow-roll parameters, which are quantum mechanically break the vacuum symmetry. And that's why one power spectrum in one direction is slightly enhanced. In exactly opposite direction, the power spectrum is slightly lowered. So that's why you have one little bit more and another one a little bit less, and the difference is non-zero and it is K dependent.
And why there is only one point in this plot?
Why there is it?
Why there is only one point in this
This
plot?
one.
Yeah.
This one is what observations so far could pin down more
1 point.
precisely 1 point. 1 point. Okay, well, of course, this is combination of understanding low multipole data. So, well, when you go to low multipoles, because the people, when observational people look at the angular correlations, okay, angular correlations are related to low L, and the low L, the range of low L are related to K. So here in the Fourier space. So this is 1 point is basically what observations say. This is for the, okay, for this particular mode K, okay, which is nearly 10 times smaller than the so-called inflationary pivot scale where NS is measured. So at that particular K, there is a point which has some uncertainty, which is given by this. And then there is other data which says that, okay, well, this has to decrease for higher values of K, but there is no precise number with good confidence level. So the observations only indicate this point to be at 3.3 sigma. Okay, here we give a complete prediction match. Of course, this matching this point is not kind of fixed by anything. So we, yeah.
Thanks.
Okay, so
5 minutes.
5 minutes. Okay, fine. Please, 5 more minutes. Maybe I'll just wrap it up about black holes. Okay, so okay, well, one more thing is this construction gives a completely new observable, which is called the hemispherical asymmetry of tensor power spectra. This is model dependent. We predicted for the Stravinsky and Higgs inflation, but this is a completely new observable no one has seen. So, but we propose this is something. If it is seen, then probably it's an indication that our construction of quantum field theory in crowd spacetime is interesting. Okay, in 5 minutes I will wrap up on black holes. What this direct sum quantum field theory will mean. So when we talk about black holes radiate. They are unstable quantum mechanically. This is what basically Hawking told us. There are two problems associated with black holes, which is basically the unitarity and information paradox. Here, the thing I talk about the unitarity is basically those specific entanglement entropy exceeding the black hole entropy, which is kind of a something that has been worrying physicists. And the concept is, according to Hawking calculation, is that the particle, any quantum state in the interior of the black hole is entangled with the exterior of the black hole, the particle at the exterior of the black hole. This is described by the direct product of Hilbert spaces of the two particles. And information problem occurs because what is inside and what is outside are completely independent of each other. So this, in the Hawking calculation, the assumption is that, okay, well, black hole takes everything, and what goes inside is nothing to do with outside. So then that means you kind of have a problem with information. So you can never understand by seeing something outside, you can never understand what's inside. Fine. How the Hawking calculation goes? You have Schwarzschild spacetime, and Schwarzschild spacetime again has this discrete symmetries. Okay, if you go to R tends to infinity, you get asymptotically Minkowski, and it has the same discrete symmetries. Okay, but this spacetime is not a suitable spacetime to quantize your field. Exactly like you have inflation, you have cosmology in de Sitter spacetime. You need to go to conformal time, which gives a metric conformal to Minkowski. That's where you quantize. So here again, you go to a metric form which is conformal to Minkowski in the 2 dimensions, 1 + 1 dimension. There is a H2 sphere. Okay, this is then once you go to this form, which is exactly called the Kruskal-Jacquard coordinates, then you take your field and express it in terms of spherical harmonics. because there is a problem in the Schwarzschild space-time. Like you go to, there is horizon, or well, horizon, there is singularity, but this is a fake singularity, it's a coordinate singularity. You can remove it by transformation, the going to Kruskal Jacobs coordinates. But R equal to 0 is the real singularity, and you cannot predict, you cannot assume a GR to be valid or at this scale. So we want to work in a regime where GR is valid, so far away from the singularity. That means we need to quantize field very far away from the singularity, close to the horizon. So that's means spherical harmonics are the suitable choice. Now, if you go to interior or exterior, there are several discrete symmetries associated with Kruskal coordinates, and Hawking cuts off more than half of these discrete symmetries based on assuming there should be some arrow of time, so the black hole should collapse and form. So from all these physical considerations. But if you go to mathematically, well, quantum theoretically, okay, well, here we're talking about quantum fields, and we know precisely how to quantize field in this static space-time, and Hawking assumes that, okay, static spacetime is a good approximation, but we do not really know how exactly the collapse happened microscopically, how the quantum fields have behaved microscopically during the collapse. So that's cutting off these discrete symmetries is kind of not justified in the sense. So here we say, well, let's say we have given spacetime and we want to quantize the field and take all the discrete symmetries, but this has nothing related to classical notions. Okay, you have black hole. This describes a black hole spacetime. Okay, now I will just speed it up. So two assumptions: discrete symmetries are ignored, and there is interior and exterior are totally independent of each other. So the second point is not correct according to GR. Suppose if you have a particle, classical particle just inside the horizon and classical particle just outside the horizon, they both influence gravitationally through shock waves. These are called the gravitational for shock waves. It is a very simple calculation. If you have a particle in a Schwarzschild spacetime, particle is given by the point-like energy density delta function, and try to solve your gravity GR equations, and you get a metric which exactly gives a point-like source, and everywhere it is Schwarzschild metric. So if you have two particles which are kind of approaching each other, and then because of this point-like source, it creates a shock wave in the transverse directions, and because of this, particle just inside the black hole, particle just outside the black hole affect each other's positions by their momenta. This is called the shock wave geometry, and this exactly gives a wonderful relation between the interior and exterior field. Well, the paper already appeared last week. So what we done here is that interior and exterior field operators do not commute, and the non-commutativity is exactly related to the Newton constant and the horizon radius, and also the speed of light and the h bar. Okay, if you apply quantum mechanics to the fact that interior particle and exterior particle do not affect each other, do affect each other through shock waves. Okay, so that means this is not true. And discrete, if you take into account discrete symmetries, and if we apply our direct sum quantum field theory, which gives a picture that you have a black hole and you have a Fock space for the quantum states inside the black hole, and you have everything else outside the black hole. So you have a Fock space, and these two Fock spaces are not direct product but a direct sum. So that means the field theory inside and outside is completely independent of each other, but still there is a relation through the field operators inside and outside. This is what lesson you learn from shock wave geometry. So that means you do not have the standard entanglement entropy and entanglement. So there is no entanglement entropy, there is no Page curve, and there is no unitarity problem. And also there is no information problem either, because what is inside and what is outside are not totally independent of each other. So with this, I would like to end, and well, there is a picture to understand this, but maybe it's a good point to end. So what I the final message is QFT in crowd spacetime is important, and there are a lot of conceptual questions which are need to be understood, and I think they are crucial for quantum gravity. Surely, quantum gravity frameworks has taught us a lot about gravity at very short distance scales. So to go a step forward, maybe QFT in crowd spacetime is an important topic to investigate. And here, the direct sum QFT offers a picture which can give unitarity and no information paradoxes in the context of cosmological black hole spacetimes. And there is observational effect. Anything you do different in quantum theory will lead to some observables. So that's beauty of quantum theory. So which we kind of project and as a test for this formalism. So thank you very much.
Okay, great, Sravan. Thank you very much. Alex, you have questions? You have questions? Alex? Well,
Alexei?
you're muted, Alexei. Maybe just
Well, maybe I can put the last slide and advertise, well, in my opinion, the best book of quantum field theory. After reading it, I learned how much I don't know, and then yeah, it's a masterpiece.
It's a very good book. Well, we had already also a question. I don't know if Alex has more questions.
Do you have any question?
Well, but if we start, I think it's going to be a very long discussion about this how to understand these fields when you create it in the phi 1 or phi 2. I mean, it's not it's still not clear to me.
Sure.
I mean, for instance, let's suppose you want to do, let's suppose you're not creating particle. You want to do just Casimir effect. I want to see, I don't know, some fluctuations of fields between plates and so on. Okay, which field would you use? That you would use one field, I guess. You would not use
well, of course, if you choose, if you have ability to choose.
No, you need to do physics, right? You need to do an experiment.
Yeah, exactly. If you look at any physical systems where PT symmetry is not broken, PT symmetry is respected, you cannot tell any difference with this construction and the standard construction. You cannot tell any difference.
No,
and
if you just about Minkowski.
What?
Minkowski. Just
yeah,
about
then you cannot tell any difference. No observer.
Even in Minkowski, what you said apply that if you
can apply.
You make a choice, you break, of course. PT,
yeah. Of course, then if you choose one particular time arrow, okay, then you reduce to standard quantum field theory. That means if you have ability to choose, like like if you must be a observer quantum mechanical, because as Coleman writes, like time past and future is something for human beings, but not for the quantum theory. Okay.
No, but let's suppose you're in Minkowski, you have only one time.
Yeah, if you choose really one time, and then if you choose this one time, you already choose this Schrodinger equation. Okay, you get your standard Minkowski.
Yes,
nothing changes. Okay, you can do calculation in the direct sum QFT. Okay, just given a Lagrangian, and you compute all the vertices and calculate everything, you get the same thing.
No, what I'm asking is that, as you said that in inflation, you break PT in the background, and then since the field is PT symmetric, you will see a difference in the end in the anomaly.
Yeah.
The same can be done also in Minkowski. You can start from this combination of fields, which is PT symmetric, the way you construct it, and then you choose some phenomena where, of course, PT is broken.
If you choose something breaks PT symmetry and you follow the standard quantum field theory rules, and then you follow the direct sum quantum field theory rules, okay, then you will see the difference. Because if you have the PT symmetry breaking or CPT breaking, let me put CPT, okay, so because CPT is the full construction. If you have a physical system with CPT breaking, you will see observable effect. But standard quantum field theory is not about that. CPT is there, respected everywhere. So you cannot see any difference. And this is not exactly not only just my statement. Also, when
No, wait, what I'm saying is that, I mean, even in standard quantum field theory, Lorentz invariance is respected, but we know that we break it everywhere, right? I mean,
Lorentz invariance,
I mean, ideally is respected as a field theory, but once we choose, I mean, any experiment breaks Lorentz invariance. So you can maybe find a way to break it.
if you choose a Lorentz invariance breaking, what you will observe is that if you have n particles scattering into m particles and m particles scattering into m particles, the amplitude must be different. But this is not observed in nature.
No, what I'm saying is that, of course, it's not. What I'm saying is that you can break, I mean, the theory, of course, the Lagrangian is CPT symmetric, right? And
then you cannot break it. All the Hamiltonians are PT symmetric. You cannot break it.
you cannot break it because Hamiltonian is symmetric. That's true.
Yeah.
But what I'm saying is that even if you take the Hamiltonian for a scalar field,
It's PT symmetric.
even if you take the Hamiltonian for the scalar field in your expanding space-time, the way you define it is PT symmetric.
Okay.
Okay.
Well,
But-
because space-time is not symmetric either. So let me put it this way. When you talk about expanding, you talk about de Sitter or quasi-de Sitter?
quasi-de Sitter, the worst.
Quasi-de Sitter
Is not
course,
symmetric.
it is not PT symmetric, no. Then I say, okay, if the background itself is not PT symmetric, and if you have fluctuations moving in this PT asymmetric background, okay, they evolve differently. If you do it in the standard way, PT symmetric is respected.
Yeah, because indeed in our real universe, because of you have this quasi-de expansion,
Sure,
you will not have PT as a fundamental. I mean, you will not. I mean, your PT is broken.
Yeah.
By your background, by your.
Yes, then I provide an observable because the PT is broken by the background, and then when you talk about fluctuations propagating in this background, okay, then I give a construction which is how in one way these fluctuations can have PT symmetry breaking with the correlations. It's a geometrical effect.
No, but is it okay? Good.
Yeah.
You can put. I don't know now. In your space-time, in Minkowski, if you put some source, you break something.
No.
You break it. What do you mean? No, you break it.
Come on, you give me a Hamiltonian which breaks or not. So this is the thing. I mean,
No, you can write. I don't know now for CPT. I'm saying if you take even Lorentz invariance, if you put a source in your space-time, you break like translation invariance. You can break things like that, of course. You break translation invariance if you put a source, right? Now you can put some source.
I'm not talking about translation invariance.
No. In the same way, you can put some source maybe and break.
Yes, sure.
Artificially, yes. You can
yes,
break.
that will be a test. You can, if you can do it, and if you have an experiment to design that way, okay. I want to see the CPT symmetry breaking.
Let me ask you something.
Yeah,
else,
better,
maybe.
Alex. You can ask after that.
So I understand more or less what you try to achieve. I'm just curious because my understanding of GR or generically of Einstein idea was that you first of all you somehow erase more and more difference between space and time. So here I literally not sure I understand why you so care about this T part of CPT statement.
Of course, I'm not caring about just T part. I care about completely CPT, okay? And because what I showed is the quantization of chargeless fields, so C is not there. And all the construction is based on both parity and time reversal operation, not just one.
No, it's okay. I'm just I'm just saying that generically,
Yeah.
Since the difference between time and x, for example, is erased
Yes.
in GR, then I'm not sure I understand why do you care at all about T
Well,
inversion, but even if I understand this, I totally how to concur with what Luca was asking. Generically, in a full GR, it's not just like you have some field in some space-time, there is back reaction, placing some source, even a whatever in Minkowski space, technically speaking, makes not Minkowski space at all, at least nearby this source. What happens in your picture, and how does your picture improve our understanding of what's going on?
Okay. But your question is related to just GR, but I'm talking about quantum fields in curved spacetime. Okay, point number one. Then you talk about GR. Then I give you two examples. When you have inflation, okay, you have GR. Let me. I don't know. Maybe I will. I don't have the slide switch here, but anyway, I can just give the picture of inflation. How do you get inflation? You have GR, and you have some matter. Okay, you provide a metric and then get your background solution, which is inflation, expanding universe, giving some classically initial conditions. Then you talk about perturbations. When you talk about perturbations, you again respect these perturbations have to be solutions of GR, right? Once you understand this perturbation, then you quantize them. This is where things will start. So then you're talking about quantum fields in a given background space. So this is where the understanding differs, because it's not like in the context of inflation we don't care about the back reaction, because when you have G mu nu equal to T mu nu, background is G bar mu nu equal to T bar mu nu, and then you have perturbations which is delta G mu nu equal to delta T mu nu. So you completely solve full equations. So here I'm saying you take into take back reaction into account, but this back reaction are the quantum mechanical ones. You quantize, you have your quantum fields. How your quantum fields affect back your geometry. Let's say if you have inflationary spacetime, okay, then you write the metric perturbation, but then you quantize this perturbation. That means these perturbations are promoted to operators, okay, which give you a effective metric which is kind of quantum corrected. That's what give you all these correlations or anything, all these quantum fluctuations in a given spacetime. That's what you measure. This is in the context of cosmology. Now, you ask the question, okay, if I have something point like particle in Minkowski spacetime, there is an effect. Yes, that is true. This is what actually Toft has computed. Not Toft, Saxelberg shock wave, right? Which is exactly solving from GR equations. Now you talk about two particles interacting with these shock waves, and there is also actually something called quantum field theory of shock waves, which exactly talks about not just about Minkowski QFT, but it's about talking something like a point like energy sources in a Minkowski spacetime, which give shock waves from the GR equations. So yeah, there is a lot to be understood taking the GR solutions and seeing from the quantum mechanical point of view. If you want to quantize any degrees of freedom of GR, well, of course, GR plus matter, whatever. And no one told us how to do it, okay? And we did not measure anything that clearly says, okay, this is really quantum mechanical effect. Of course, we expect, but it's not something confirmed by observations. So here I'm looking at, okay, what are the ways to do it without going to any super modifications of GR or any super modifications of quantum theories, no quantum gravity. Okay? Just looking at within the context of GR or whatever the matter, but then understanding QFT, which is an open question.
Okay.
Okay. And maybe another thing which I don't understand is when you make some how to say, not correlation, how to say it better, when you somehow appeal to quantum mechanics. To me, quantum mechanics is construction of Hamiltonian, which usually in standard quantum mechanics is operator which has eigenvalues of energy. Now, if I go to a curve space-time, and again, it's generic in GR, there is no well-defined energy. There is stress energy tensor. I can reparameterize it anytime.
Yeah.
I mean, I can reparameterize coordinates anytime such that energy is. I mean, I even don't know what energy is. Usually associated with zero component of stress energy tensor, which may be not the case in a sense that this component can be meaningless in a sense, because it's just a tensor, it transforms with my coordinates. What do you mean when you use this kind of parallel with quantum mechanics and other stuff?
It's very simple. When you do the quantization of any field in curved space-time, okay,
Yeah.
you do not follow the rules of what GR telling you or not. You try to form a variable that effectively describe it as a time-dependent harmonic oscillator. Well, in the context of cosmology, this is example. This is a famous Mukano-Sasaki variable. Okay, well, here it is phi tilde equal to a phi. Only this thing is what we know how to exactly quantize and from the known rules, right? So this is what I'm talking about. So basically, and the only difference here is that time is conformal time. That means it's not usual Minkowski time. It basically describes about this metric. Now, if you want to do the same thing in the context of black hole, you want to quantize some field in the black hole geometry. What you do again, let me show you this. Okay. You go to this crucial manifold. Okay, then you integrate out all this y, and then you expand your scalar field in terms of harmonics. Well, this is just a classical, right? Then what you quantize here is this part, which is like a 1+1 dimensional field, and close to the horizon, it is effectively like in the one Minkowski 1+1 dimension. Okay, and then you promote it to operator, and that's what you quantize it. So we always apply the tricks we know from the standard quantum field theory, but just in terms of different variables that characterize the curved spacetime, which is basically the here U and V are the characterize the curved spacetime, characterize the Schwarzschild spacetime. Okay, now that's how we do it. And well, in the context of black holes, we basically quantize something near the horizon, and then ask about vacuum very, very far away, which is Minkowski, and with Bogoliubov transformation, we say, there are particles here. That's how we do it. We always follow the same rule, same game of harmonic oscillator or Klein-Gordon field, but the game is just to go into a different coordinate systems with different variables. So your question is a very grand question, but that's not what something needs to be understood. Maybe it's a long goal, but then to achieve that goal, we have to master with what we are doing at the very basic level.
Okay, I think it's a good time to maybe thank Sravan again.
Thank you very much
For the talk and for answering the question. So yeah, we will meet again next. Well, actually, we have to discuss when to start. Yeah, again.
Maybe you can stop live stream, Alexei. So
yes, let me stop it.